Hello everyone. Uh, Getting back to the subject of contact analysis in finished element stress analysis. Uh, I am back on this simple example that I have showed you in the previous video. In the meantime, there was some concerns about whether the loads are too big or there are other problems with this case. So I have prepared two reference analysis to show what is the correct solution for these two cases that I have here. So I have prepared two additional positional representation. Position 3, which represents this assembly when this force applied on the edge acts in this direction, so pulls this plate against those two. So in such case, as you can see here, the pin is misplaced until it touches the edge of the hole in this fixed plate, and in the other side of the pin, the inner plate, I will change its color so you could see better. Let's say smooth red. Okay, so we have the inner plate displaced, and the inner plate pushes on the pin. The tangent point is exactly on the middle plane of the plate. In the positional representation 4, the situation is opposite. So it is the positional representation for the case when the force is pushing on this plate. So it is displaced in the other way, so the pin touches here, and basically the middle plate pushes on the other side of the pin, so the pin is, let's say, compressed. And one I have prepared and solved the assemblies, solutions analysis before, so not to waste time now. So the analysis number 3 is following the positional representation number 3, as you can see here. So it is the case when this force pulls the plate away. In this case, the other plates are excluded from simulation, and in static analysis 4, the situation is opposite. So it is the case when this plate is pushed against the pin and against the fixed plates. Boundary conditions are as before, forces as are before. Now, if we consider the load here is 10 kilonewton. 10 kilonewton is really 1 ton of force. This pin is 18 millimeters in diameter. This plate is 10 millimeters thick. So loads applied here are very small comparing to the capacity of these elements, and I have it solved. So I will just start with the displacement. As you can see here, the displacement is the maximum displacement is 0.0518 millimeters. So it is proper solution. So this plate doesn't move, the pin deflects slightly. I am showing undeformed. I will show you actual, and I will show you, let's say, like that. So the mesh is quite coarse, so we are seeing the displacement for the big elements, because I didn't want to lose time for the remeshing and solving. So if we examine the deformation, the deformation is as expected. I will just show you that view half section. I will just move it slightly so we can see here. So we can see that the deformation is really equally spread about the edge of the plate, and decreases, and in the area where the plate pushes the pin, it is slightly smaller. So we have properly solved the case. If we consider the stress, then we can see that the stress is not on the high level. If I have cut the scale on the 50 megapascal, but we can surely do better. If we set maximum, we are getting the value of 837, but we will not see anything because it's a numerical peak. So we will be, let's say, 100 megapascal. So as you can see, the stress is distributed as expected. So it is concentrated here where the plate pushes the pin, and it is slightly smaller for the fixed plate because there are two plates, so the load spreads about over two plates. As for the pin, this is really a point contact. So, but we can see here that the contact analysis, this is all done with the separation no sliding contact. So we can see that in this case the contact analysis didn't fail, it worked okay, so this is a proper solution. If we go to the second scenario where this force pushes against the plate, we have the results as expected. So as you can see here, the deformation here is smallest, and basically it's evenly spread over the plate. If we consider stress, I will replace it with the 100. So we can see that the stress is also in little values. So there is no way that this would not converge because of the loads that are too big. The loads are small for this case. They are only to show the results. So basically the problem is all these cases that I have showed before are very similar. They all use separation contact for the pin and the plates. They all use forces perpendicular to the side, and basically the boundary conditions are the same. Only the difference is that in those previous analysis I haven't displaced the pin and the plates to the position where they are touching in such a way that they are working in given scenarios. So compression and also compression, but the force directed the other way. So the question is why the contact analysis fails for simulation 1 and 2, and once it is working correct for the simulation 3 and 4. So in simulation number 1 we have a straightforward situation in which we have just actually aligned plates, actually acting force. We have contacts that have been assigned automatically, so the software have found the contact between this and this phase, but it didn't follow the contact during the obtaining the solution. So this basically is a problem with this analysis. It is not the load, it is not the convergence, it is not meshing, it is not other stuff involved in finite element analysis. It is, this example is about contact behavior only, and I think we should stick with this problem, not trying to mix other stuff like meshing, optimization, or whatever it is. It is solely about why this contact fails in some cases, and in some cases it works as expected. So this is the question for this analysis.